Okay, let's go ahead and take a look. Okay, in this first one, we have the acid chloride reacting with the Grignard. Right, and so we know that's going to react with the carbonyl. But after it reacts once with the carbonyl, right, we would have this. And then will a ketone react with the Grignard? Yes, right? So the product of this will be adding 2 of the Grignard alkyl groups, right? So we add 2 of those. On the second one, we have an acid, carboxylic acid. We're adding heat. Carboxylic acid with heat. Sometimes you'll see minus H2O. What does minus H2O mean? I'm removing water, right? So one of the ways to drive this reaction forward is to remove water. I can do that through several means, but sometimes you'll see minus H2O. You ever see minus H2O? Just means I'm trying to get water out of the reaction. And what this creates, right, is the anhydride. So if we remove water, we just put those 2 alcohols together. So this is one of the synthesis for acid anhydrides. Okay, questions about this one? It only works with symmetric, right? That's one of the issues. On this one, we have the amine, and then we have the pyridine. So this one might have thrown you off because you might have been used to seeing it this way. Right, 2 equivalents. And if I draw that big enough, you'll be able to see it. 2 equivalents, right? So therefore, if I draw it with pyridine, the pyridine is just acting as the second equivalent. Right, so what I need is two equivalents. One's going to add, the other one has to act as a base. Okay, and I make the amide. Okay, questions about that? Okay. So if you didn't see the email, a couple of things. First, the quiz. Quiz 2 is going to start after class. It will extend till 10 o'clock. A couple of modifications. One, right, 1 question at a time. Right, so if you're used to seeing all of them, it's going to be 1 question at a time. There was some concerns about exam security. I looked at a few things and there might have been a problem with exam security, so we'll do that one. The other is the answers are not going to show. Okay, so you won't get the answers right away. Well, you know if you got it wrong, but you won't know what the right answer is. Okay. I can go back in and turn that on later so you can prepare for the final exam. Okay, but you won't see that until I do that, which will probably be next week. Okay, yes, ma'am. Yes, sir. Yeah, yeah, okay. It's hard to do that. And if you try to go back, it might flip up on you, but yeah. Okay, exam 2, we're gonna change the date. And I really think it would be too much of a rush to do it on Tuesday. So next Thursday. Okay, I will extend the hours a little bit. I'm waiting for some information to see how long I'm doing that. And so it might start a little bit before class. Last time it started with class. I might start it earlier with class because I do know that some of you have an exam for your lab same day. That could always happen, right? We don't talk to each other. The lab exam could have been on Tuesday and I could have made everybody stay by moving it to Thursday. But I do think it's better for y'all to have that extra 2 days to study for the exam. So it'll be there, same thing, 1 question at a time. So what you see on this quiz will be what you see. And then again, I'm not posting the answers right away. You'll see those when I turn on that toggle a little bit later, okay? All right, for exam 2, while we're there, let's go ahead and talk about what we're gonna cover. So go back and check my email. It tells you what the quiz will cover, and hopefully you looked at that. For exam 2, we're gonna go back to 1812, okay? And then we're gonna go all the way to 2012. So we're not finishing out this chapter. So we're going to make it through esters today, but we're not going to get to amides. Okay, and that'll be the line. So when we get to the end of esters, that's 2012. That's where we're going to stop. And then after, for the next test, we'll get to amides, because I want to make sure that we get enough practice. Tuesday is really going to be a review. So we're going to work some problems together and try and go through. We've covered a lot of reactions. And so today we're going to cover esters, but then on Tuesday, we're just going to look at questions that could be on the exam. Okay, so it'll be a whole day of review. Questions about the quiz or the exam? But yes, ma'am. Yeah. Okay. I understand. Makes it a little tougher. Okay. It won't be locked, but I don't believe you can go back. Okay. All right. Let's look at preparation of esters. So same process. Any other questions? All right, so we looked at preparation of esters from the acid chloride, right? So this is a review from earlier. And we can do with this with pyridine, or we could have done it, you know, with excess ethanol, and what we'll get is the ester. And if we look at the mechanism on this one, the alcohol acts as a nucleophile onto the carbonyl. Pi bond breaks, so the pi bond is our leaving group. That ends up with a tetrahedral intermediate, this one. Okay. Then here our pyridine, right, can be our base, so we'll pull a proton. Electrons go over. And then electrons come down, kick off our chloride. And we just saw this on Tuesday with the acid chloride. So that's method one. Method two, we'll take an acid, we'll react that with a base, and then we can add a good nucleophilic electrophile, such as a primary carbon or a methyl. And what we're doing here is, in the first step, right, we're deprotonating the proton. That's now making our acetate or our carboxylate. And then that carboxylate is a good nucleophile. Bless you. So the nucleophile does an SN2 reaction, right? We attack the carbonyl carbon, leaving group leaves. And I run out of space. And we get the ester this way. Okay. Okay, so first we make the carboxylate, right? Then we react it with the electrophilic. This one works great whenever the carbon group is a good SN2, right? So what we're looking for here is an SN2 style process. So if I had a tertiary group, this is not going to work well, but a primary, a methyl, potentially a secondary, it's going to work fine. Okay. The third way to prepare ethers. And this Fisher has a C. This one has a name, Fisher esterification. Here we're going to take the acid and we're going to take the alcohol with an acid, okay? And the way this one works is the first step is actually protonation to activate. So we're in acid conditions. So the first step is going to be protonation of that carbonyl. Then the alcohol can attack that carbonyl. That ends up with this tetrahedral intermediate. Then we need a proton transfer. We could use generic base or we could use more methanol here. Going to the non-protonated tetrahedral intermediate. And then I'm going to use the protonated species. So now we get a proton transfer. Either one of those two alcohols would work. The OH groups here would work. I'm going to use this one because it's closer. That's going to give me the protonated alcohol. And that's reversible. And then now we can have the lone pair come down, right, and kick off the water, which is a good leaving group. We now have the methyl here, right, and water could come back and attack that and go backwards. Or the water could pick up that proton, regenerating our acid. So we have a catalytic system with the acid. Okay, to get our ester. So if we look at this process, right, the whole thing is reversible. So Fisher esterification more or less is going from the acid to the ester by driving it forward with an excess of the alcohol, right? What if we had added an excess of water and acid to an ester? Same process, we're just driving it backwards to the acid, okay? So excess of methanol, we go forward to the ester. Excess of water, we go backwards to the acid. Now, of these three methods, right, if we look at this first one here, right, I'm not using an excess of methanol, right? I'm not using an excess of my alcohol. So this is a good one whenever you have a very specific alcohol. So if you had a large alcohol with stereochemistry and everything, and you don't want to waste a lot of that, this is a good one. If we look at the second one, this one also works well, right? We can, if we look at this one, right, if we had a very specific alkyl halide that we wanted to react with, that work good. 3 is good when what? You're making a methyl ester or an ethyl ester, and methanol and ethanol are cheap, and you can add a bunch in there, right? So when my ester portion, the methyl or ethyl or whatever that was attached to it, is pretty straightforward. So the Fischer esterification is a good process there. Okay. The second one won't work with tertiary groups, right? But the third one could, because you're never reacting at the tertiary group. So a few things to think about when you have these three different groups and which one would work where. Okay. So reactions of esters. So saponification. And this one has a special name, and I'll give you a reason why in a second. Okay, so saponification, that's actually a base promoted hydrolysis. Oh, should be an oxygen right there. Sorry, not a ketone, ester. Okay, so what's happening in this one? This can come in and kick this off. That gives us a tetrahedral intermediate. Then the tetrahedral mediate. This electrons can come down and kick off the methoxide. If it came down and kicked off the hydroxide, I'd be going backwards, right? So kicking off the methoxide, I progress to the next step. And now I'm going to put the methoxide there, but it could have also been the hydroxide. Right. Now this is a good base. What does a good base do with a good acid? Bases deprotonate acids, right? So here's a base, there's an acid. Now, notice this arrow. Is there any way for this to go, is this going to go backwards? No. The acetate is too stable, it's not going to deprotonate our ethanol, so we stop there, right? So this is the end of the first step. Then in the second step, that's where we bring in our acid, because we want to make the acid, we don't want to leave it as the acetate. And so this then picks up a proton, we get a proton transfer, and we end up with this. So this is base promoted hydrolysis. So going from an ester back to a carboxylic acid, and it's non-reversible because of this step here when we create this, right? It is two-step process. We add the base, then we follow with the acid. Now, the reason that it's a saponification is that this is what you use when you make soap. Natural soaps, not phosphates or ammonium salts, but just old-fashioned soap. You take and you use lye. So lye is lithium hydroxide. So my grandmother used to make lye soap out of pork fat. You take the fat and you render it, more or less you boil it and get all the pieces out. Then you add the lye, right? And then the lye will do the hydrolysis, right? Because you're in water, and you end up with the glycerin. And then you end up with 3 of these long fatty chain groups. And then these groups when you want the soap to react, when I take that hard lye soap and put it in water and I put a little mechanical action in it, what does it do? Makes suds, right? So you take soap, put it in your hands, and move it around, you get suds. What that's actually doing is creating micelles. So you get this little negative charge up here with this big, long, fatty chain. And the way soap works is you make micelles. So on the outside is this polar head, right? And that's the acetate molecule. Right? This is water, right? So the outside is hydrophilic. The inside is hydrophobic. And those are both one word, right? Hydrophobic, hydrophilic. So when you have soap, what's happening is you're actually taking this micelle and you're putting it on your skin, right? And it disturbs the, what it does is it allows the oil from your skin that has the dirt and stuff attracted to it, go inside the micelle. And then once it's inside that micelle, right, the micelle is water soluble, then it's going to rinse off with water, right? The way this disrupts bacteria and other things, like viruses, is that you can trap the virus inside, but in bacteria, what's actually happening is this micelle, this saponification group, can actually disrupt the bilayer phosphate lipid layer and just make the more or less the bacteria go right. So you're disrupting its protective layer, and then you can destroy the bacteria that way, right? So this is, so it gets its name saponification from the fact that it's making soap, right? And that's the Latin phrase for that. Now, the interesting thing about soap is that you can make soap in several ways, right? My grandmother took pork fat. They would have these big pig kills in South Louisiana. My family was Cajun. They started as sharecroppers. So my grandpa was a sharecropper. And when they kill a pig, everybody would come together to help kill the pig because they didn't have a lot of refrigeration. But you also then had to do something with all the fat and everything. And so they would make lard, but they'd also take some of it and make soap. And they would use lye. And it's easy to make lye in South Louisiana because you can get lye by taking oyster shells and burning them. When you burn oyster shells, it'll make lye. So you just put that into the big cauldron, right? And poke that around and put it in some little wooden blocks and you could make soap, right? But the interesting thing about it is that soap wasn't really known to the ancient world outside of a few particular passages, right? The Romans didn't have soap, right? But they had baths, right? So how did they take a bath without any soap? Well, they had hot water. They had all these really cool hot water and stuff. But what they would do is they'd put oil on their skin, and they would take a special wooden bar or ivory if you're really rich, right? And you would then just scrape it off, right? So you'd put the oil on your skin. Now, if you were wealthy, what kind of oil would you use? Use olive oil, right? If you weren't wealthy, you'd use what? Pig fat, right? So you can smell, they didn't smell very attractive after this, right? But it does turn out that if you take ashes from a fire where you have burnt an animal, what happens to wood is you make potash. Potash is basic, right? And if you render an animal, so leave it on there until you've burned up the entire animal, what happens is the fat of the animal falls down into the ashes. Well, if you put the fat of the animal in the ashes, well, that's fat, right? That's this. And the potash from the burnt ashes, well, that's a base. What happens when you add water? You start to create soap. So some of the behaviors of cleansing rituals They're referred to in the Bible, but they're also referred to in some other ancient writings, actually was creating soap, right? But the really odd thing that I always, and I tell this every year because I find it odd, is that the Romans were known for baths, but they never had any soap. Now, if you wonder what you're doing, so if you want, people didn't wash their hairs a lot, right? And now we wash our hair all the time. I don't have to because I don't have as much hair. But you know, what do you do after you wash your hair to make sure it looks good? Well, you add a conditioner. What are you actually doing there? Modern soaps are really good at doing what? Cleaning, right? They're really good at cleaning, and therefore they'll strip all the oil off of your hair. So what are you doing when you add conditioner? And I'm not saying this is not to gross you out and not to get you for not doing this, because I like it when people don't smell like they haven't bathed in months, right? Which was normal 150 years ago. What you're doing is you're stripping all the oil out with the soaps, right? And nowadays we have a lot more ammonium soaps and some phosphate soaps. They're being phased out because they're environmentally problematic. But you're stripping all the oils out, and then you have to replace the oils. Now, modern times, you don't usually replace the oils with pig fat or olive oil, but you do with some kind of plant oil, right? So if you look at the main ingredients in conditioners, there will be some type of fat or oil molecule. The only difference between a fat and oil is what temperature that it changes, right? So a fat and oil are more or less the same thing. If it's liquid at room temperature, it's an oil. If it's a solid liquid temperature, we refer to it as fat. In Polynesian countries, which my wife is from Palau, you actually would use what they put in their hair all the time was coconut oil, right? And so that was actually something you do for, and what they were doing was they were cleaning their hair by putting in the olive oil in there, and they were conditioning it. So anyway, so that's soap. Okay, questions about the process? Okay, the other hydrolysis is acid hydrolysis. And this, as I pointed to earlier, right, is just going to be the reverse process of the Fischer esterification, right? So what we're doing here is, if we have an ester and we add water and acid, we go to the acid. If we had the acid and we added an alcohol and acid, we go back to the ester, right? So this one here is the inverse of this one, right? So work this mechanism in the reverse, and you'll see that we'll get the same process. Now, on acid hydrolysis, right, this is always reversible. So one of the things about acid hydrolysis versus base promoted hydrolysis is that acid hydrolysis is reversible. I have to drive it forward with water. With base hydrolysis, it is not reversible. So ammonolysis, and that's just a fancy word for breaking with ammonia. And again, we want two equivalents here. So we can go from an ester to an amide. Same conditions we saw with the acid chloride and the acid anhydride. Notice with our hydrolysis of esters, are they different than the chloride and the anhydride? Yes, with the acid and the acid chloride and acid anhydride, we just needed water. With esters, I either need a base or I need an acid. Okay, so I'm having to up that difference. But with the amine, right, going from the ester to the amide, no need to change my reagents. Okay. Reduction of esters, right? And when you saw the lithium aluminum hydride, they did show an ester back in the book, so this is a little bit review. And it's the same as what we saw for acid chloride. So lithium aluminum hydride, right, And we need an excess of that, excess, right? And then water, we're going to end up with the primary alcohol. The mechanism is like the chloride. We have our aluminum hydride reagent. It's going to be a hydride donor. It's going to attack the carbon of the carbonyl. Pi bond is going to be my leaving group. I get the tetrahedral intermediate. I've got the ethoxide is a good leaving group. So the oxygen electrons are going to come down, kick off the methoxide. This forms the aldehyde. And an aldehyde will be reduced with the aluminum hydride. And then second step, we add our water to give us our proton to get us back to the alcohol. Okay, so same nucleophilic substitute, ACL substitution we've seen before. Now remember with our acid chloride and our acid anhydride, let me put or here. I could use a lithium aluminum trialkoxyhydride, right, followed by water to give me the aldehyde. We can do a similar thing with esters, but we can't use the same reagent. So for esters, instead of using this lithium aluminum trialkoxyhydride, I'm going to use something called dibol. Now, depending on what book you're using, they have several different, you can have dibol, with an L and an H. But dibol is what our book uses. And what dibol is diisobutyl hydride. So it's got the single hydride reagent. It's almost always shown as dibol, right? Not shown as its reagent, but notice that it has two bulky alkyl groups and the hydrogen. And what this does is do the reduction. So it'll stop at the aldehyde, okay? So the first step mechanism is fine, but then the dibol doesn't react with the carbonyl. So we stop at that group. So we can do the same reaction with the chloride, the anhydride, and the ester, but we have a slightly different reagent between the acid chlorides and the anhydrides than we have the esters, okay? So again, make some flashcards, make sure you learn those. We can also do Grignard reagents. And again, we need an excess. We need at least two equivalents in excess. Oh. Okay, so if we look at the mechanism, it's going to be similar. It'll be the same as what we saw for the chloride, but seeing this over and over again, it's going to start to stick. So we get this one. Then that tetrahedral intermediate, the oxygen negative is going to come down, kick off the good leaving group. The good leaving group is going to be the methoxide. That gives me the ketone. Will ketones react with Grignards? Yes, they will. So Grignard comes in and attacks that carbonyl. And then we add our water to give us our proton. And again, the way we'd recognize these is that we would have two of the same R groups attached, right? So if we look at this, we have two of the same R groups. Questions about these reactions? Yes, ma'am. The dibol works for esters. The lithium trialkoxy aluminum hydride works for chlorides and anhydrides. Okay, so it's slightly different. So the dibol works better with esters. If I use the lithium aluminum trialkoxy, I'm not going to get a good yield because it doesn't react with esters well. Both of them stop at the aldehyde, but one is better, right? And then you potentially might, the dibol doesn't work very well with the chlorides and the anhydrides. So it has to do more with, one will give you 80 to 90% yield, and the other one will give you 20% yield. And so it's just, you've got one reagent that's better than the other, okay? You don't see that very often, but in this case, because you're particular, you need it to react enough with the starting group, but not the second group. Both of them won't react with the aldehyde very fast, but then they have different reaction rates to the first one, okay? Questions? The other thing with the anhydrides, let's look at this since it was brought up, right, is that if we look at our esters, and let's say we use 3 different conditions. So here, let's use sodium borohydride. Here, let's use lithium aluminum hydride. And here we'll use dibol. Okay, take a second, think about these 3, and think about what your products would be. I'll give you a hint, they're not the same. So when we look at these three, sodium borohydride, right, will react with ketones, but it's not a strong enough reagent to be a hydride donor for esters. It also won't work with anhydrides, won't work with chlorides. And as we'll learn for the next exam, it wouldn't react with amides, right? So that means that our product here would be reduction of the ketone, but not reaction with the ester. Lithium aluminum hydride will react with both ketones and acids, right? And in this case, it's going to reduce both of those down as far as it can, which means it's going to reduce the ketone to a secondary alcohol and it'll reduce the ester to a primary alcohol. And then dibol reacts with acids to create aldehydes, right? So it stops at the aldehyde. But if it stops at the aldehyde, will it also stop at the ketone? Yes, right? So it reacts with the acid, but not the ketone. So I can go to the ketone and the aldehyde. Questions about these three? Yes, ma'am. Yeah. Okay, so the first one reacts with the ketone, right? Sodium borohydrides react with ketones and aldehydes, but does not react with esters, chlorides, and anhydrides. The lithium aluminum hydride will react with ketones and aldehydes and acid chlorides, anhydrides, and esters. And then the last one here, dibol, right, is specific for esters, right? It reacts with esters best to turn them into aldehydes. But since it won't react with aldehydes, it won't react with ketones. Any other questions? All right. Okay, so that's where we are for exam 2. All right, so that gets us from chapter 18.12 through 20.2. So a few things to notice, right? When we look at our esters, okay, we had a way to convert those back to the acid, and we had several ways to convert that to the ester. We had a way to take the acid and turn it into the amide. We had a way to turn the ester into the aldehyde, ester into the alcohol, ester into the Grignard, right? But notice that we weren't able to turn it into the anhydride, right? We're not going backwards, and we didn't have a way to turn it into the chloride, right? So we're not going back up the river. We also didn't have a Gilman reagent for esters, right? So we had a Gilman reagent that added a methyl where the chloride was, and a Gilman reagent that added a methyl or alkyl group where the anhydride was, but we don't have that for esters. So again, this kind of pinwheel chart, they're in the book, but I would suggest you draw it out, because if you draw it with your own hands, you have a better chance of remembering it. Okay, so we've covered a lot of reactions, and although we've done some try this, I think that it's best, we're going to use the rest of the day and we're going to use Thursday to really try some synthesis, try to recall this, talk about how to watch for some things. And so let's go ahead and get started with that, right? I'll let y'all fill this in on at home. So let's try this. Give me some products. And again, some of this will be knocked in the rust off. It's been a few weeks. Okay, so let's take a little while, try these three. Again, feel free to talk to your neighbor while we do this stuff. Or look through your notes or look through your flashcards. I'll try and give you all plenty of time for these. So remember, on the test, you're going to have about 2.5 minutes per question. 2.5 to 3 minutes. Okay, to help you get thinking in the right way, the first one is an NAS, that stands for nucleophilic aromatic substitution. The second one is going to be an oxidation. And the third one is going to be an electrophilic addition followed by a tautomerization. Okay, I'll give you a little bit more time. Again, feel free to talk to your neighbors about this, look at your notes, book. Okay. Let's go ahead and take a look. Okay, so we can get through some of these. On this first one, right, what does nucleophilic aromatic substitution mean? That means I'm going to do a nucleophilic aromatic substitution. So I'm going to use a nucleophile to substitute on an aromatic. What's my nucleophile? Well, it's the hydroxide here, right? And so what am I going to substitute? The nitro or the chloride? Well, which one's a better leaving group? Chloride. So I'm going to substitute the chloride. It's been a while, so let's look at the mechanism on that one. So we have our chlorine. We've got the nitro. Remember that these work best with very specific groups, right? And what it has to do is it has to have a halide, right? Chloride or bromide or iodide. And let's keep our color scheme correct. And it needs a strong withdrawing group, like a nitro, right? So we get a negative here. And then the negative charge comes back, right? Kicks off the leaving group. This is how I end up with my phenol. But why do we have to add acid in the second step? Well, phenols are very acidic. So as soon as I make that, I lose a proton. the negative, the nitro, and then if we add and then second step, we reprotonate. Okay, so we haven't asked questions about this one yet, so you might have not spent some time studying it. Remember, make sure you're thorough when you're looking at all of these. Okay, so that's the first one. Okay, the second one is an oxidation. Well, this is actually a review from Organic 1, but we also covered it in synthesis of ketone, so make sure you know it, right? So oxidation of a secondary alcohol is going to go to a ketone. And then this last one, again, is review from Organic 1, but we looked at it in the preparation of ketones. Oh, one too many carbons. Right, so we add the OH, right? So that's the electrophilic addition, but it's an enol. It's got an alcohol attached to a double bond, which tautomerizes to the ketone. Questions about these three? Knocking off a little rust around the nucleophilic aromatic substitutions. What's the other mechanism we looked at the end of that chapter? That was the elimination reaction, right? So the elimination and process, we go through a benzyme. So make sure you review that. Okay, let's look at picking some reagents. Just take a little more time. Look at these three, give me the best reagents. Take a little bit more time. Try and get all three of them if you can. Okay, the first one is an oxidative cleavage, right? So what's happening is we're actually breaking that bond right there. So if we look at 1, 2, 3, 4, 5, and 6, here I have 1, 2, 3, 4, 5, and 6. So what's happening is I'm breaking that carbon-carbon double bond and adding oxygens to both sides. Right, to do that, I'm going to need ozone, followed by a reductive workup, such as something like dimethyl sulfide, or I could have used zinc and acid, and that will give me this. So ozone, again, review, but it makes an aldehyde, so it was an organic one, but you need to bring that back up. The second one, we're making an acetal. To make an acetal, all we need is the appropriate alcohol and an acid catalyst, right? So, you know, you could put the H like this, or use tussle acid, toluene sulfonic acid. Okay. Questions about that one? The last one, we're making the enamine, right? And for the enamine, we're going to need a secondary amine, right? And we need, again, a trace acid. So we could have used the toluene sulfonic acid, and we'll get the enamine. So this is, note that this is a secondary amine. Secondary amines result in enamines, primary amines result in imines, right? So reaction is about the same, but they end up giving us two different possible products. Okay, questions about these? Okay, helpful? Okay. So let's do a few predict the products. So let's take a little time. One of the things I noticed of office hours, you're having trouble with condensed forms. So anytime you see a condensed form, draw it out, okay? What you see in the book and what you see me do is show you pictures in the condensed form. Don't try and make your mind do it. Draw it, right? So don't try to grasp at it. Just go ahead and redraw it. So here's what that aldehyde looks like. It's a 3-carbon aldehyde. Okay, a little bit more time. Okay, the other thing I noticed is that you're trying to go through steps without really drawing out the steps and thinking about each one of them. So we'll take a little bit longer. If you didn't think about what those intermediates are, please do. Okay, let's go ahead and take a look. On this first one, we have a thiol, right, with acid. The thiol is going to react with it like an alcohol, right? So instead of getting the ketal, we're going to get the thioketal or thioacetal. So that means we're going to end up with this intermediate after the first step, right? We're going to end up with that product. Now, I could hydrolyze that to go back to the carbonyl, right? Or in the case of rainy nickel, what type of reagent do we have when we usually have hydrogen and a metal? Reductive, right? So this is a reduction. Now you'll notice that sometimes the book doesn't show hydrogen, it just shows rainy nickel. I like to show hydrogen and rainy nickel. It actually turns out that rainy nickel is nickel and hydrogen together. So you don't have to add it extra, but I like to show it, and the book often shows it, but every once in a while you'll see rainy nickel. So if you see rainy nickel, don't get confused. Rainy nickel is actually a process where you bubble hydrogen through nickel to make a porous rainy hydrogen absorbed nickel process. So I noticed that in the book, just thought I'd point that out. So a reduction process, what's going to happen in reduction? Well, we're going to reduce something. So if we have a double bond to 2 electronegative atoms, now we get rid of those, right? And so the product of this one is just the cyclohexane. That's a really hard way to get cyclohexane, but you get the point. Right, the next one, we have the thionyl chloride. Thionyl chloride is what we use to convert acids to acid chlorides. Okay, now in this one, if you looked at this and you have no earthly idea what's going on, think about what your process is. I got phosphorus with a lone pair. What is phosphorus with a lone pair going to do with an electrophilic carbon? Well, that's going to attack that, kick that off. All right, so I'm going to end up with the phosphorus attached. What happens if I add a strong base? What do strong bases do? Pull off hydrogens. Where's the most accessible hydrogen here? Could it be next to the big positive charge? Yes, right? So therefore, this is going to make that a negative. Make that a positive, right? This is my phosphorus ylide. And again, thinking about, okay, when did I see phosphorus ylides? I saw phosphorus ylids with Wittig's, right? And my Wadsworth-Emmons reactions, right? So if I was Wittig, and then if I react that with my aldehyde, what did the Wittig do? Well, if Wittig made a double bond, what specific stereochemistry? If it's unstabilized, then does this look stabilized? Do I have any carbonyls over here? No. Do I have any oxygens over here? No. So this is unstabilized. Unstabilized goes to Z, right? So therefore my product, I'm going to want to add a double bond where that phosphorus was, but now because it's both unstabilized, Z is going to be my favored product. Okay. So whenever you see condensed forms, always draw them out, even when it's on the online homework, or if you see it on the quiz. Again, the quiz and the exam, you can have the paper there. Just don't call your neighbor, right? Have some integrity, but write things out on paper, right? Do that. And then if you have multiple steps, think about what each step is possibly doing, right? Not everything is broken down into steps, but most of them are. So 85% of things we're doing, you're going to be able to see the steps. Okay, let's do 3 more real quick. Get y'all ready for the quiz. Give me the reagents. Okay, so let's go ahead and take a look. On the first one, that's the Baeyer-Villiger reaction. For the Baeyer-Villiger reaction, notice that I'm inserting an oxygen between the carbonyl and one of the carbons. I'm going to use my old friendly peroxy acids for this. What is the thing to really remember when you're dealing with the Baeyer-Villiger? This one's symmetric. What if it hadn't been symmetric? Okay, what I want to look up is the migration preference. Right? So tertiary over secondary over primary, right? Hydrogen being the first. Okay. So make sure you look at that when you're every time you see a Baeyer-Villiger, try to recall that migration preference. Okay. Next one, we have the acid chloride going to the alcohol or the ester. Remember, with acid chlorides, they're very reactive, so I don't need acid or base or anything. All I need is a simple alcohol, right? So with anhydrides and acids, alcohol is fine. As we'll find out with amides, we've got to add something else to get us there. And then the anhydride here, we're going to the ketone, right? So I've added this group. This is a Gilman reagent. The Gilman reagent, whatever you've added, right? 2 of those are next to a copper lithium, right? So the Gilman reagent is this cuprate. right? And this does a coupling reaction. So whatever is attached to the carbonyl needs to be in those parentheses, and I need 2 of them. Questions about these 3? Yes. If you put, oh, MCPBA, yeah, MCPBA would work, right? So MCPBA, the T-butoxide, the methyl, the trifluoro, any of those would work. Okay,